Okay, so the first topic we're going to look at is limits. And with a lot of these topics in calculus, especially in the beginning, you just need all of the information all at once. So it's always hard to figure out exactly where to start. So I'm just going to start with this pretty classic example, and we'll just build on that. So the function given is x minus 2 divided by x minus 2. And the question written there is, for what value is the function undefined? Well, it's undefined when the denominator is 0. So I would say at f of 2. Because at f of 2, we get 2 minus 2 divided by 2 minus 2, which gives us 0 over 0. So since there is what's called a discontinuity at x equals 2, we can't simply cancel and say f of x equals 1. And that's because, if you look at this function, that is equal to 1, except where it has a discontinuity, which is at f of 2, which is right here. So if we graph that, let's see if I can graph this. I'll just use this red. This would go by 1, right? So that function is going to be 1, just what I said previously, everywhere except for x equals 2. So at x equals 2, we're going to have what's called a hole. And this is what the function would look like if we were to graph it. So it's discontinuous at x equals 2. So here's something else. I'm going to put a different color here. So I'll write that out. The function has a hole at x equals 2. And in this case, we call this a removable I'm going to spell that correctly though. Discontinuity. And we call it a removable discontinuity because we can cancel x minus 2 over x minus 2, and that is 1. So we have removed the discontinuity if we cancel it. Okay, so that's a really basic example of a discontinuity or a function with a discontinuity. So here's the next question. But what does the function seem to be approaching at x equals 2? So in calculus, what we're all going to talk about a lot are what things seem to be doing. So they're not actually doing them, they just seem to be doing that. And in this case, if you were to head towards x equals 2 coming from the right, it seems like the function's going to just continue and go to the value of 1 at x equals 2. And from the left, it looks like it's going to head towards a value of 1 at x equals 2. And when I say value of 1, I'm really talking about y equals 1. It's heading towards y equals 1 as we approach x equals 2. So it's written out here. So if we approach, right down here, if we approach x equals 2 from both the left and right sides of the function, f of x appears to be heading towards what? Well, we just said it. It was f of x equals 1. So f of x and y are interchangeable, so we're just saying as you go towards x equals 2, the y value seems like it's going to be 1. So if that's the case, if it seems to be heading towards the same value from the left and the right, we say the limit exists. Okay, let me get rid of this box. Okay, so the way that we'd write this out is here. Okay, So if the question we're asking, what's the limit as x goes to 2 of x minus 2 divided by x minus 2? It equals 1. So this is the way to officially write out the problem. Okay, in a little box, it says this: for a limit to exist, the following conditions must be met. The limit of f of x exists if x approaches c coming from the negative side. So that would be from your left. Or 2, the limit of the limit as x goes to c from the positive side of f of x exists. And so that would be coming from the right. And if those two numbers are the same, then we say the limit exists. So these conditions all have to be met. The left limit has to equal the right limit, which is what this is saying in this step here. Both limits are the same, therefore the limit exists. And for a lot of these things, like this box, it's highlighted in red because that's one of those really important things. You have to have that down and memorized perfectly. It's one of those types of things. Okay, so that's a basic introduction to some limits. We're going to look at these in several different ways to look at limits. So we're going to look at a couple of different ways here. Okay. Now, predictable, that's just kind of a word through there. It's not really a technical term, but some limits are predictable. So if you look at the limit as x goes to 2, I'll try to highlight this so you can see where I'm pointing. We're looking at this part. If you look at the limit as x goes to 2 of x squared plus 1, and we graph that, so you wouldn't always have to graph these because you'll see a pattern here. Let me get that. Okay, well, as x goes to 2, x goes to 2 is here. So essentially the right-hand limit would be heading towards, as we head towards 2 from the right, and as we head towards 2, x equals 2 from the left, what value does the function seem to have at x equals 2? The way that I look at this, and that the arrows I drew, that's just coming from the left and right. But since we have a slope on this thing, it makes a little more sense to look at it like, well, this is coming from the right, and this is coming from, and this is coming from the left. So what function value does it seem to be at x equals 2? Well, it seems to be at 5, right? This is at a height of 5. Okay, so the limit as x goes to 2 of x squared plus 1 is going to be 5. So I'm going to write that out here. So the limit as x goes to 2 of x squared plus 1 equals 5. Now you can see that if we just plugged in a 2, we would get the value 5. So some limits can be evaluated directly. And that means that you could just plug the number in. So if the function is continuous at all places, you can just plug the number in and get the limit value. So x squared plus 1, it's a continuous function. There are no domain restrictions or anything like that. So you can just plug the number in. It's going to be 5. And that would be the limit value at that point. Okay, now this is an important point here. So we just did that. We did the limit as x goes to 2 of x squared plus 1 is 5. And I just said, if you plug in the number 2, that also equals 5. So these things are true, okay, and they are equal to the same value, but they are not the same thing. So they say different things. F of 2 equals 5 is the y value when we plug in a 2, or is f of x evaluated at 2. The limit as x goes to 2 of this function is 5, is what the function approaches it to. So this first statement here is saying that is what it is, and this statement is saying that's what it appears to be. So those are saying very different things. It's just a small, well, it's not really a small point, it's a big point, but just be aware that although you're evaluating limits by plugging numbers in, it doesn't mean the exact same thing. Okay. Let's do a graphically one. So basically we're going through different ways to evaluate limits depending on what limit you're given and in what form it's given. So here you have a piecewise function. It's just some unnamed function, so I don't, I just drew that picture. I don't have an equation that goes with it. So if you were to be asked something like, what's the limit as x goes to 3 of f of x, then what do? Well, f of x is this function, and 3, that's giving you an x value. So from the right, it's heading towards the value of 6, you can see that. And from the left, it's heading towards the value of 6. So this limit value is 6. So if you look at each of these statements, the limit as x goes to 3 of f of x, that's saying what y value is the function approaching as we head towards this x value. Okay, so let's do another one. Okay, let's go to -3. So the limit as x goes to -3 of f of x. Well, on the left, that limit value appears to be 3. So I'm going to check it like this. So this little negative sign I drew there, that's saying coming from the negative side. So this is the left-hand limit value. Didn't mean to delete that. Of f of x, well, that is heading towards the y value of 3. And on the right, as we head down this way, that appears to be heading towards a y value of 5. Okay, so the left and right hand limits do not exist. Or no, the left and right hand limits are not the same, therefore the limit doesn't exist. So if you go back to this box statement here, it says for the limit to exist, the following conditions must be met. The left has to exist, the right has to exist, and they have to be the same number. So if we go down here, look at that again, the left hand and the right hand, they do appear to be heading towards these values, so those limits exist, but since they're not the same, the overall limit, if I write this here, this is a does not exist. So a D and E does not exist. Okay, so that is a graphical way to evaluate limits. So if we continue here, okay, yeah, so I did this already on a calculator. For this particular one, I entered the function. So this is a numeric, finding one numerically. First thing you'd always want to do is plug the number in. So if I just plug in -3, well, the denominator is definitely going to be 0, so I know that's not good. And if I plug in a -3 up here into the top half, that's also going to be 0, because it would be 9 minus 15 plus 6. So that's going to be 15 minus 15, and that's 0. So we get this 0 over 0, so we can't do that. So from a calculator, I'm going to go ahead and open this up. Okay, so I entered the function into my calculator, and I did have to change the table step. So automatically, when you enter a function and pull up a table, it's going to increment by 1. If you notice in this column that I'm tapping around on, that is incrementing by 0.01 each time. So sometimes you have to change that to really clearly see what's going on. So the stuff below -3 would represent, we're talking about a left-hand limit, and the stuff above -3, this would be your right-hand limit. So if those appear to be approaching the same value, then the limit exists. So this one on the left-hand limit is really consistent. It's going -1.05, -1.04, -1.03, and so on. And so it looks like it's heading towards -1. On the right side of this, it looks like it's heading towards -1 as well. So we would say that that limit exists, and the limit is in fact -1. So if I fill those values in, this is just taken from the calculator. You could also manually enter these values into a calculator if you don't know how to use the table function, but that's a lot slower. Okay, so if you look at the left and right here, I'm going to pull up red. From the left, we would say the limit as x goes to -3 of f of x appears to be -1. And then from the right side, we would say the limit as x goes to -3 from the positive side also appears to be -1. And since those are equal, we say that the limit exists. So the limit as x goes to -3 of this function is -1. Okay, so sometimes these are tedious to do because you do have to either enter the values into a calculator. You're entering values close to -3, but not -3. So it's just tedious, even if you have to pull up a table. I know Desmos is really good with these problems. I think the table function is pretty clear. So that's probably your best bet. Let's look at just one more example. Okay, so the last example we'll look at today is the limit as x goes to 0 of sine pi over x. So I have already pre-entered this into my calculator, just like the last one. And if you look at the table here, so the values below 0, so all these negative values, they seem to be matching the values on the other side of 0, so in the positive. So these are the same number on both sides of 0. However, one's negative, one's positive. And so in this case, it's actually easier to just look at the function itself on a calculator because you can see what happens at 0. The left side is heading towards -infinity, and the right side's heading up towards +infinity. So if the limit at x equals 0 over all of this function doesn't exist because those are going in opposite directions. They're not approaching the same value. So that's a really easy problem when you can look at a picture of it. So we would say this does not exist. Okay, so that's your last example today. So hopefully you can get started on the homework. If you need help, just make sure to attend office hours or shoot me an email. Thanks.